This conference will now be recorded.
Hello everyone, the topic that we are going to discuss today, necessity of second law of thermodynamics, then second law of thermodynamics, entropy gives free energy and net work done by the system, and effect of temperature on spontaneity, and also some related problems. So we have already finished first law of thermodynamics, but there is also a second law of thermodynamics. But before going to detail of second law of thermodynamics, we have to know why second law of thermodynamics is required. What is its requirement? It means that first law of thermodynamics is not enough, so that is why you have to take the help of the second law of thermodynamics. Fine. So what are the things that we will not be able to know from first law of thermodynamics that we have to see first? So if we consider first law of thermodynamics, it places no restriction on the direction of a process. And satisfying the first law, it doesn't mean that the process will occur. So if you look at the picture, here we have hot container. So when there is a hot container and there is a cold surrounding, heat will be transferred from this to this. And that is possible. But the reverse is actually not possible. But if you simply consider first law of thermodynamics, this type of possibility you will not be able to predict. Okay, so first law of thermodynamics, it places no restriction on the direction of the process. That is the problem. Fine. So heat transfer from hot container to cold surroundings is possible, but reverse process, though it is satisfying first law, that means simply satisfying first law, it doesn't mean that it will occur, because here also first law is satisfied. If you simply follow the first law, then the reverse process, that is from cold surrounding heat transfer towards hot container, that we never observe by absorbing heat from surroundings on its own. So the reverse process by absorbing heat from surroundings on its own does not occur spontaneously. So this process is fine, but the reverse process, that is cold surrounding, gradually it will lose more and more heat and it will become more and more cold, and the hot container will become more and more hot. That is not possible. That means the hot container, it cannot absorb heat from the cold surroundings and itself is becoming hot and hot, hotter and hotter. So that never observed. That we never observe, right? But still it is satisfying the first law. So there must be another law which should restrict this type of direction. So some direction should be restricted, some direction should be allowed. So this means that we need some another law from which we will be able to predict the direction, right? But first law is having failure. Another process, if we see, air leaks from balloon on its own if there is some leakage. It is possible. But the reverse process, that is automatically, suppose there is a balloon and automatically air is entering the balloon on its own, that we never observe, right? But that is also possible according to first law, and first law is not putting any restriction. So what we have to do, we need another general principle to identify whether a process can occur or not. That is the direction. From different types of natural experiences, what we can say, it can be said that certain processes are spontaneous. For example, from hot container to cold surroundings, heat is transferred. That means hot container will gradually become cold and cold surrounding, that will gradually become hot. These type of processes are spontaneous. Then if you look at this picture of balloon, that is filled balloon, suppose there is some leakage and gradually it is shrinking in its size, that is spontaneous, but the reverse process is not spontaneous. So some processes, there is a preferred direction, so that is what is spontaneous, right? So this is non-spontaneous, but the first one is spontaneous. This is spontaneous, but the reverse one is not spontaneous. Okay, another point, if we consider first law, it tells that there is exact equivalence between various forms of energy. So it is another way of saying the first law, because first law you can say in different ways, and different ways I have already explained in detail. So one of these statement, you can say that there is exact equivalence between different forms of energy. So heat gained that is the amount of heat gain, that should be equal to heat loss. But what happens practically, it is not possible to convert the heat energy into an equivalent amount of work. So there is some loss of energy, and you will not be able to convert the whole amount of heat energy into an equivalent amount of work. That is not possible practically. But from first law, it is saying that heat gained is equal to heat loss. So this is another thing which we cannot predict from first law. So these are the 2 points. First points, it is mentioned here that there is no restriction we are getting from first law based on the direction of a process, and another point is heat gain is equal to heat loss. That is also not always true. So practically it is not possible to convert the heat energy into an equivalent amount of work. So the second law of thermodynamics helps us to predict whether the reaction is feasible or not. So that is the necessity of second law of thermodynamics, that it helps us to predict whether the reaction is feasible or not. That is, you will be able to understand whether it is spontaneous or not. And that is the direction of the flow of heat that we can understand. Another point which we can understand from second law is it tells us that energy cannot be completely converted into equivalent amount of work. So this is the first point. This is the second point. These 2 points you will not be able to predict from first law, but second law we can do so, right? So it means what? It doesn't mean that first law is not required. Obviously it is required. That is the main point is whether a process will occur or not. That depends on when it satisfies both the first law as well as the second law of thermodynamics. Then only you can say as a whole that whether it will occur or not. So it doesn't mean that first law is not required. Obviously it is required, but we also need second law. Otherwise, complete prediction for a process you will not be able to do. Okay. Now, when we talk about second law of thermodynamics, we have to know what is spontaneity. Now, what is spontaneous process, that you have already seen in the last slide. We have seen that a filled balloon, if there is a leakage, then it will gradually shrink. So that is actually spontaneous process. But the reverse process, that is a shrinked balloon, then air is gradually entering in the balloon, it is becoming filled, that never occurs. So this is non-spontaneous. So spontaneity means having the potential to proceed without the assistance of external agency. So that is why when there is a balloon and there is a leakage, so gradually it will shrink in size. But the reverse will never occur. So there is no spontaneity. If you want to do so, suppose from a shrink balloon, if you want to fill it, obviously you have to give some effort. So it is not occurring without the assistance of external agency. We need some external agency. But the first process, from filled balloon, there is a leakage, it is gradually shrinking in size, that is spontaneous. We do not need any external agency. However, it does not tell about the rate of reaction or process. Remember, it is true that we are talking about spontaneity before going to second law of thermodynamics, because this is based on spontaneity. But don't mix it with rate of reaction or process, because rate of reaction or process, it is not, we never talk about rate of a reaction or process in thermodynamics. That is completely, it belongs to another chapter, which is kinetic theory, right? So spontaneous means there is a no external agency required and the process can proceed without this assistance, but it is not talking about rate. That is different thing. Fine. So do not confuse these 2 things. Rate of the reaction, that we can know only from rate constant, which is completely different chapter, topic of different chapter. So a spontaneous process is an irreversible process and may only be reversed by some external agency. That means, suppose if I am saying that this is point A, this is point B, so movement from A to B, this is spontaneous, this is irreversible. So it can move without any external agency's assistance. But if you want to reverse it, now you need some external agency, because the reverse process, that is from B to A, this direction, that is not spontaneous. So that is why we need external agency. Okay. Now, when we will actually state the second law of thermodynamics, we will basically do it with the concept of entropy. So first we have seen what is spontaneity. Now we have to know what is entropy. So second law of thermodynamics, it introduces another state function which is entropy. We have seen different state function, right? That is internal energy, enthalpy, different state function we have seen. Now we are going to introduce another state function which is required before going to second law of thermodynamics. So what is entropy? It is a measure of molecular disorder, or you can say it is a randomness of a system. So when I'm saying that entropy of system 1 is higher than system 2, it means that system 1 is more random, more disordered compared to system 2. Now, how we will express it in the form of mathematical expression? Thermodynamic definition of entropy is concerned with change in entropy that occurs as a result of a process. How we will express it? You will express it as, that is, change in entropy ds. So for small change you can use a small d, that is letter d, or you can use del sign for finite changes. Thermodynamic definition of entropy, change in entropy. Basically you cannot say what is value of S, or that is absolute value we are not talking about. We are talking about difference in entropy. That is, suppose that is state 1, there is state 2, and the difference between these two states entropy. Entropy for state 1, entropy for state 2. Difference is ds or dS, right? So we are talking about that. We are not talking about absolute entropy. So change in entropy ds, that is equal to dq reversible divided by T. So it occurs as a result of a process and it is expressed in this way. Basically D should not be there because as it is a path function, we never use D or del, right? So for, that is heat absorbed or liberated for a reversible process divided by at which temperature. So we are dividing it by temperature, and if you consider SI unit, it should be joule per Kelvin, because for Q it is joule and there is denominator, there is temperature. So it is joule per Kelvin, that is the unit for entropy. So for any spontaneous irreversible process, so this is for reversible process, ds is equal to q reversible by t. But now when it is spontaneous irreversible process, now it is greater than sign. So that is the difference. Okay. So here in the first case it is equal to sign, and in the second case, when if it is spontaneous process, except spontaneous process, you can write it directly equal to a q for reversible, but for irreversible it will be greater than sign. It is equal to heat energy exchanged divided by the temperature at which the exchange is taking place. Now this is mathematical expression, but how we can what is the significance, physical significance of entropy, that we have to now understand. Second law of thermodynamics, we have already seen that it tells that the whole amount of internal energy of any substance is not convertible into useful work. So total change in internal energy, it is not that you will be able to convert it to some useful work. That is not possible. That we have already seen from second law of thermodynamics. That means a portion of this energy is available to do useful work and rest of the portion is not available to do useful work. So just think about del as if it is combination of two parts. One part is available to do useful work, another part is not available to do useful work. Now the part, that is the remaining part of the energy which we cannot be used for useful work, you can call it as unavailable energy. So it is not available, and that unavailable energy is actually entropy. So you can say in another way that as if it is unavailable energy per unit temperature. Okay, because Q reversible or irreversible divided by T, that is actually change in entropy. So we will say that change, that is total amount of internal energy, that is present in any system or substance, you will not be able to convert it to useful work. So some amount you will not be able to convert, and that amount is unavailable. So that is why it is unavailable energy per unit temperature. So that is this is actually entropy. That is the physical significance of entropy. Now we will go to the actual statement of second law. Though it can be said in different format, you can see in different textbooks it is stated in different manner. So here we will state it on the basis of entropy. So it is entropy statement of the second law of thermodynamics. The second law of thermodynamics can be expressed in terms of entropy. The entropy of an isolated system increases during a spontaneous process. Entropy of an isolated system. Isolated system, there are different types of system: open, isolated, closed, remember. So where it is isolated system, entropy increases during spontaneous process. So this is one way you can state it. Another way also you can state it, that a spontaneous process. So that is when we are starting the statement, we are saying it is spontaneous process. The spontaneous process is accompanied by increase in the total entropy of the universe. So it is basically same statement, you can say in different way, accompanied by increase in total entropy of the universe. So we are considering universe as if it is isolated system. So we will see now it for irreversible process. An example of irreversible process is spontaneous expansion of gas. There is no spontaneous compression possible, right? But one spontaneous expansion is possible, and that is the example of irreversible process. So for irreversible process, del S total, you can also say it as if it is del S universe. So del S total subscript or universe as subscript, it is always greater than 0. Remember what we have seen in this slide, ds for irreversible or spontaneous process, it is greater than q irreversible divided by t. So it is a positive quantity. So that is why it is mentioned here, it is greater than 0, it is positive quantity. Now del S total, you can also write it as it is del S system plus del S surroundings. It is greater than these two quantities. That means del S universe, sorry, this I'm trying to say that total is basically combination of these two. Okay. So universe, whether you say universe or del S total, it is combination of these two quantities. It is greater than 0, or you can say that this is greater than 0. Okay, so another different way you can say the same statement, that spontaneous expansion of a gas, which is just an example of irreversible process, and maybe any other irreversible process. So del S total for this type of irreversible process, it is always positive quantity. Now del S total, it is basically combination of del S system and del S surrounding, or you can say that del S universe is greater than 0. Now if it is reversible process, example is melting of ice. Suppose there is melting of ice, now ice is converted to liquid water. Now if we can extract it, if we can remove it from liquid water, then again we can convert it to ice. Now in this case, del S universe, that is actually equal to 0. Now del S universe, you can also write it as del S system plus, so I am just writing in place of del S universe, del S system plus del S surrounding. In short, I am writing SU+R, which means surrounding. That is also equal to 0. Now, if you bring this quantity to right hand side, it will be this expression. That is del S system, that is actually equal to minus del S surrounding. But that is only true for reversible, because in case of reversible process, del S total or del S universe, that is directly equal to 0. It is not positive, it is not negative, it is directly equal to 0. But when it is a reversible process, you can say that del S total is greater than 0, or del S universe is greater than 0, or del S system plus del S surrounding is greater than 0. So it is several way you can say this. Fine. Another state function we will learn today, which is Gibbs free energy. Remember, when we have discussed physical significance of entropy, we have seen that some amount of total internal energy of the substance, some amount you can do for use, you can use for useful work, but some amount is we will not be able to get useful work from that internal energy. So there is a part which is unavailable, and that is actually entropy change. But there is a part from which you can get some useful work. So this point we will now focus. For an isolated system, it is the total entropy change, del S total, which decides the spontaneity of the process, whether it is greater than 0 or equal to 0. Depending on that, you are now able to understand whether it is spontaneous process or not, whether it will be reversible or not. But remember, though this statement is true, but most of the chemical reactions, if you simply consider chemical reactions, they fall into the category of either closed system or open system. So closed system, that is energy transfer possible. Open system means mass transfer, energy transfer, everything possible. Isolated system is nothing you can exchange, whether it is energy or mass, nothing. But if you actually consider the practical examples of different types of system, it is basically chemical reaction we mostly deal with. And chemical reactions, we cannot consider it is occurring in isolated system because there is always exchange of energy. So it is either occurring in closed system or open system. That means, though this information is important, that total entropy change for isolated system, from this we are able to understand spontaneity. But remember, when you are actually considering the practical examples of chemical reactions, there is no isolated system. That means, though this statement is important, but actually there is no application of it, because we are dealing with closed system or open system. So there are changes occurring in both enthalpy as well as entropy. So what to do? So we need some another state function which can combine both these quantities. And this new state function should be such from which we will be able to predict whether it is spontaneous or not for all these chemical reactions, because it is occurring in closed system or open system. So in this new state function, which is basically this Gibbs free energy, it is expressed with the letter capital G. You will see that it is a combination of enthalpy as well as entropy. So this point is related to del S. Now these 2 points, what it is saying, see, it is saying that exothermicity, that is whether a reaction exothermic or endothermic. Suppose it is exothermic, that means del H is negative. Del H is negative. It is exothermic. It is liberated. It is true that it favors spontaneity, but that does not mean, it does not guarantee it. It is true it is favoring spontaneity, but this much information, suppose you know that a particular reaction is exothermic, heat is liberated, but that doesn't mean that it has to, it favors spontaneity, but it doesn't guarantee it. So it is not the ultimate information from which you can predict whether it is spontaneous or not. So del H also not helping us, del S also not helping us individually. So we have to combine them. Neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change for this type of systems. So what to do? We need a new thermodynamic function which is Gibbs energy or Gibbs function capital G, and it can predict now the spontaneity of a process. So it must be the combination of these 2 quantities. So the importance of this function is that it is developed by Josiah Willard Gibbs, who originally termed this energy. That is, initially it is called as available energy. Remember, total internal energy of a substance, some amount is available, that is, you can convert it to useful work. Some amount is not available, it is called unavailable. That you will not be able to convert to some useful work, and that is actually del S. But this available energy, that is, initially the name is available energy, that is actually Gibbs free energy. So if you know Gibbs free energy properly, you will be able to predict how much available energy, that is how much part of internal energy you can convert to some useful work. That is why it is available energy. So the expression of G is, as it is combination of H and S, but T is also there, that is temperature. So G is equal to H minus Ts, and Gibbs free energy, it is extensive property dependent on amount of the substance. Now suppose there is a system, state of the system changing from state 1 to state 2, temperature is constant. So when temperature is constant, it is G2 minus G1, that is the difference. H2 minus H1, that is the difference between the two states. And T common, S2 minus S1. So all these quantities, you can now write it as del G equal to del H minus T del. So this is the ultimate expression for del G. Now, from this expression, next we will see, depending on del G is negative or positive or 0, we will be able to predict about the spontaneity of a system, that is chemical reactions, where it is occurring in closed system or open system. So for this type of system also, now we will be able to predict spontaneity, which is not possible if you only considering del S, or if you are only considering del H, you will not be able to predict. You have to combinedly see the effect of del H and del S, and that is actually del G. So del G is equal to del H plus minus T del S, that is fine. But how it is related to reaction spontaneity, how you will predict the spontaneity, that we have to see now. So del S total is equal to these two, that we already know, because universe or total is combination of system and surroundings. There are two parts. Now when it is reversible process, equilibrium, then del S total 0, that we have seen. Similarly, for an equilibrium process also, del G is equal to 0. But what about irreversible process? When it is irreversible process, spontaneous process, we know that del S total is positive quantity. It is greater than 0, right? Now, if it is greater than 0, come to right hand side. So for a spontaneous process, del S is greater than 0. Okay. Now, in place of del S total, what we will write? We will write del S system plus del S surroundings. Okay. Now, del S system plus del S surroundings. In place of del S surroundings, this quantity we will write in this way. Del H surrounding divided by T. Because remember, del S is Q by T. So in place of Q, now we are writing enthalpy change for surrounding. So now this part is fixed. We have not changed it. System is written as SIS, and this is del H surrounding divided by T. So this is also equal greater than 0, positive quantity. Now del H surrounding, that is actually equal to negative del H system, because the amount of heat gained or lost, if you are considering for a surrounding, or reverse situation for system, obviously for the other part. There are basically two parts in the whole universe, surrounding and system. So for surrounding, whatever amount of heat is lost, then system it will be gained, or vice versa. So that is why whenever it is del H surrounding, it is always equal to minus del H for the system. So in place of del H surrounding, now we will write minus del H system. So when it is minus del H system, now the before the expression, that is a negative sign. Now multiply all these quantities by T. So it will be T del S system, and T will be cancelled here. So this is also greater than 0. Now we have already seen that del G is equal to del H minus T del S. So when you are writing it in this way, that is T del S minus del H. If you remove this negative, it is basically minus del G. So see here, minus sign is taken common. So this quantity, so that we can write in this place del G system. So ultimately what you are getting? You are getting del G system, that is negative change of del G system, that is positive. That means you can also say it in another way, that del G system that is lesser than 0, or this should be negative. Now mostly though it is a subscript we have written system, but for simplicity we generally omit it. So it is simply written as that del G should be negative sign value. Then it means it is spontaneous. So now you can predict whether a process will be spontaneous or not from the sign of del G. It must be negative. So now we can say for spontaneous process del G should be negative, and for non-spontaneous process it should be positive. And remember, when it is equilibrium process, it is basically equal to 0. So three conditions we are getting: spontaneous, negative, non-spontaneous, positive, and for equilibrium process it is 0. So as del G should be negative, that means del H minus T del S, this quantity also should be negative if you want the process to be spontaneous. Now del H system, it is the enthalpy change of a reaction. So this part you can also put the subscript system. For simplicity it is not written. It is the enthalpy change of a reaction. And what about the second part? T del S is basically the energy which is not available to do useful work. So see here, the unit of this total quantity, that should be the unit of joule, because del S, if you remember, its unit is joule per Kelvin, but now you are multiplying with T, that means Kelvin will be cancelled. So del S unit is also the unit of energy, that is T del S. Together the unit is joule or kilojoule, but it is the unit of energy, and del H is also joule or kilojoule. That means as a whole it is energy unit. Fine. So T del S is the energy, because the unit is energy. It is that energy which is not available to do useful work. Remember what we have already discussed. It is the unavailable work. So T del S system is that part of energy which is unavailable to do useful work. And del H system is the enthalpy change of a reaction. So when you are subtracting T del S from del H and you are getting del G, this is actually the net energy available to do useful work. So the unavailable amount you are subtracting from the total amount, and now you are getting that amount which you will be able to do useful work. And that is why it is also called free energy, because this is only that amount of energy which is available to do useful work. So it is also called free energy, gives free energy or free energy. Fine. So the relationship that we have just learned, that is del H minus T del S, that is actually del G. Based on this, we'll solve this question. Data given for the following reaction: iron oxide, solid physical state, carbon, graphite. There are different types of form for carbon, graphite, diamond. It is mentioned here, it is graphite. Then product side we are getting iron, metallic iron, and carbon monoxide. So FeO is basically reduced by carbon, and we are getting carbon monoxide and iron. So for this reaction, FeO and C, these two are reactant. I am writing R. These two are product side. So del H naught value, standard state, in kilojoule per mole, that is mentioned for all the four compounds or element, and del S naught in joule per mole per Kelvin, that is also given for all these four substances. From this we have to find out the minimum temperature in Kelvin at which the reaction becomes spontaneous. So basically you have to find in which temperature del G should be negative. Fine. Now in this case we will consider, that is it is not clearly meant, it is simply written spontaneous. So what we will do, we will write this expression del H naught T del S, it is equal to 0, because it is asking at which it becomes spontaneous at minimum temperature. So directly you cannot write greater than 0, as we are trying to calculate, we are trying to find out the minimum temperature. So we will write this expression that it is equal to 0. So minimum this temperature you have to give, because if you do not providing this temperature, suppose you are providing temperature lesser than this, then obviously it will not work. So we will write it in this way. Now if you are writing this in this way, it means del H naught is equal to del S naught. Now T is equal to del H naught divided by del S naught. Okay. Now individual del H naught values for all these are given, but we have to find out del H naught for the reaction. So for that we have to consider all these quantities. So we will come back to this equation. Now what we will do, del H naught for the reaction, that is actually first consider Fe and CO, that is these two are basically product. So consider these two first. So it is 0 and minus. So 0 and minus 1105. Now come to the product side. So sorry, reactant. This is for product side. This is for reactant side. So for reactant side, what we have? We have minus 266.3 plus 0. So ultimately you will see we will get it as 155 kilojoule per mole. Similarly, in the same way, if we find out del S reaction standard state. So first do it for product side, 27.28, 197.6. 27.28, 197.6 minus. Now these two all are positive. So after calculation you will see we will get 161.65 and unit is joule per mole per Kelvin. Be careful about the unit. Here it is kilojoule, here it is joule. So when you will put it in this expression, obviously kilojoule you have to convert to joule. So T is equal to del H naught. We will put this value 155.8 multiplied by 10 to the power 3. Now it is joule per mole divided by del S naught reaction. This is basically reaction, because total for all the substances when you considering you are getting it for the reaction. This is already in joule. 963.8 and nearest is 964 because it is integer answer. Okay, so 964 Kelvin, that should be the minimum temperature at which the reaction becomes spontaneous. Okay, so if you are having temperature lesser than it will not work. At least this temperature or greater than this only it will work. Fine. Gives free energy and net work done by the system. So we will relate these two. How? Let's see. For any system when it is at constant pressure and constant temperature, this expression we already know. Now in place of del H you know it is del U plus P del V. So in place of del H you can write this expression because of this relation. Fine. Now from first law of thermodynamics we know internal energy change is Q plus W, and from second law of thermodynamics we know that del S is Q by T. So what we will do, in equation 1 we will put in place of del U we will put Q plus W, and in place of del S we will put Q by T. So putting this value of del U and del S, these two value put in equation 1. So see equation 1, now we have written Q plus W instead of writing del U, and instead of writing del S we have written Q by T. T will be cancelled. So it is minus Q plus Q. You are left only with W plus P del V. If you bring negative sign both sides, it is negative of change in Gibbs free energy, negative del G. that is equal to minus W minus P del V. Now this negative sign containing W, it is basically work done by the system. We know it is negative. So work done by the system, and now you are subtracting P del V. P del V is basically the mechanical work done by the system. Okay, so when you are subtracting it from the W, you are getting minus del G. So what is the significance? Come to this side. So P del V is basically mechanical work done by the system, and it is basically expansion against a constant external pressure as example of mechanical work. So this is basically the significance of P del V. What it means, that is what P del V means, it means mechanical work done by the system. And W is basically the maximum total work that is possible for the system to do. In both cases there is a negative sign because it is work done by the system, whether it is mechanical work or the maximum total work, whatever. So when you are subtracting it, that is a mechanical work done by the system, when you are subtracting it for W, that is actually decrease in free energy. So decrease in free energy minus del G, it is accompanying a process taking place at constant temperature pressure, because we have already mentioned initially it is constant temperature and pressure. So this minus del G, that is decrease in free energy, that is equal to maximum work obtainable from the system. This is a obtainable work, but that doesn't mean you will be able to convert this whole, you will be able to get this whole amount of work, because from second law we have seen we are not able to convert the total amount to work. So there is some unavailable work, there is some available. So the maximum work obtainable from the system, which we are considering W, is equal to the maximum obtainable from the system other than the work of expansion or non-PV work. Okay, so when you are subtracting P del V, that is basically the non-PV work, that is the remaining amount is non-PV work. So W is the total quantity, you are subtracting from W the mechanical work done. So the remaining amount is basically the maximum work you can obtain. You cannot obtain more than this. Okay, it is true that the total internal energy we cannot convert to work, but maximum work obtainable, that idea you can get from del G. So the significance of this expression is that is Gibbs free energy, how it is related to net work done. The decrease in free energy minus del G, that is equal to maximum work obtainable from the system, except this work of expansion, which is another way of saying that is mechanical work. Other than mechanical work, or you can say it is the non-PV work that you can get. So other than work of expansion, it is written or non-PV. Don't think that work of expansion is non-PV work. It doesn't mean that. Other than work of expansion, that means other than mechanical work, that is actually the non-PV work. So or is written, but don't think that work of expansion is same as non-PV work, because work of expansion is basically PV work or mechanical work. So without work of expansion or without PV work, the remaining non-PV work, that is actually the maximum work obtained, and that you can understand from minus del G. So this is a relationship between Gibbs free energy and net work done by the system. Now this expression del G R means, you can also omit this, R specially means reaction, Rxn or R, whatever you write. So from this relationship, we will try to see what is the importance of temperature on the spontaneity. So different cases may be there. So first see, suppose the first condition will apply where enthalpy change negative, that is it is exothermic, and del S is positive. So when I am writing it here, the expression del G is equal to del H. From simplicity I am omitting the subscript. So under this condition, if this is negative and this is positive, under this condition, positive means this negative sign will still be there, and there is already a negative sign before del H. So whatever is the value of T, the whole quantity will always be negative. That means del G will always be negative, whatever is the value of T. So it is spontaneous at all temperature. This is the conclusion you can draw. Example is this reaction where del H is negative, del S is positive. Because from 2 moles of O3 you are getting 3 moles. So here del S is positive. So you can easily understand why del S is positive or not, because randomness is increasing. From 2 moles now the quantity is increased to 3. So 3 minus 2 is positive. Product side higher number of moles. So del S is positive. So just by looking at the reaction you will be able to understand whether del S is positive or not. And heat liberated, so that is it is exothermic. So this is the example for this first category. Now, if both del H and del S negative, that means now before del H there will be a negative sign, but del S is also negative. That means this sign now it will be positive. What it means, if you want del G to be negative, obviously temperature should be very low. Only when temperature low, this total quantity will be very low. That means this quantity will be high, because now there is a negative sign before del H but positive sign here. So if you want del G negative, temperature must be low. So it is spontaneous only when temperature is low. But suppose T is very high, then this total quantity as a whole, as it is multiplied by del S, as a whole it will be very high. So numerical value of T del S, it will be greater than del H. So ultimately del G will be positive. So under this condition, when both del H del S negative, temperature also high, now it will be non-spontaneous. So under this condition where del H del S both negative, the condition should be such, if you want del G to be negative, you should maintain low temperature. Example is adsorption of gases. This is a physical process, but this is example where del S is negative, del H is also negative. Next possibility is both positive. Both positive means now the whole quantity is positive. That means whatever is the value of T, it is it is positive. Okay. Let me write it. So del H is positive, del S is also positive. That means now there is a negative sign before T del S. So now we want this numerical value of this quantity to be positive, because only then, as there is a negative sign, and if this quantity is very high, then only del G will be negative. So when both are positive, under this condition, if you want the reaction to be spontaneous, temperature must be high, because now we want this quantity to be high. But suppose T is very small, T del S is small, that means the numerical value of T del S now lesser than del H, and as a result del G will be positive. So it will be non-spontaneous, low temperature. Example, melting of a solid. Okay. And when del H is positive, del S is negative. Del H is positive, del S is negative. That means this is also positive. Now, temperature low or high doesn't matter, because this whole quantity is always positive. So that is why it is non-spontaneous at all temperature. So this reaction, H2O reacting with oxygen, we are getting hydrogen peroxide. This reaction, del H plus, del S negative, and it is non-spontaneous, whatever is the temperature. Fine. So these are the effect of temperature on the spontaneity of a process. Depending on del H, del S, positive or negative, there may be these 4 possibility: minus plus, minus minus, plus plus, or plus minus. Now important point is, though we are saying that from this sign of del G we will be able to predict spontaneity, but some practical things we have to keep in mind. What are practical things? It is assumed that del H and del S will remain the way indicated for all temperatures. So here we are assuming that low temperature, high temperature, del H will remain fixed, because del H, del S remaining fixed, then only we can give this explanation. But what happens, del H and del S, though we are assuming it will remain the way indicated for all temperature, but it is not always necessary. Okay, it may change sometimes. The spontaneity of a chemical reaction, it is only the potential for the reaction to proceed as written. So from spontaneity, suppose you are able to predict del G is negative or not, and now you are saying it is spontaneous or not. Yes, it is giving you the idea that whether there is a potential for the reaction to proceed as we are expecting. But there are some other factors, that is rate of such process. Now rate we do not talk about in thermodynamics. It is all about kinetic theory, completely different chapter. But rate also plays some role. It may be that del G is negative and we are saying that it is spontaneous, but maybe the rate of the reaction is very slow, which is nothing to do in thermodynamics. So rate of such processes is determined by kinetic factor, which is completely outside of thermodynamic prediction. So here we are just talking about thermodynamic prediction, which is just giving us some idea about the potential, whether there is potential for the reaction to be spontaneous. But even after being spontaneous, maybe that now from kinetic theory we are seeing that the rate is very low. So though there is a del G value negative, but practically the reaction is so slow that ultimately it will not. So there are several things we have to consider, but only from thermodynamics you can predict up to this. But don't forget there is also kinetic factors involved. That is also that is combined effect of kinetic and thermodynamic factor we have to consider. Now we will apply this temperature effect for this expression, that is del G is equal to del H minus T del S. So here you can see, suppose there are independent process, temperature is fixed 300, process A, process B, process C, process D. Temperature is always 300. But del H is changing for all these four processes, del S is also changing for all these processes. So what we'll do, we will use this equation for all these four processes. We will put the del H value, del S value, and T is 300. So 4 times we have to do it, and in each case we will see when we are getting negative sign for del G. So suppose out of 4 you are getting only in one case negative sign, that means number of non-spontaneous process will be 3, because only in one case you are getting negative, only one process is spontaneous. So if we do this for all these 4 processes, so for the first process, del G, that is del H, this part is del H, because in all these values of del H we are multiplying 10 to the power 3. It is given in kilojoule, be careful about the units. So we have to multiply 10 to the power 3 to convert it to joule, and then this is del H part, then there is a minus T del S. Now 300, it is always fixed, that is mentioned already. Now for the process A, it is minus 80 minus plus. For the process B, del S is plus 40, so there is still negative sign. For process C, negative positive, and for the last process it is again positive, so there is a negative sign. So what we will see after calculation, though full calculation you don't have to do, just look at this, you will be able to understand whether it will be negative or positive. So it is 25,000 and it is 80 into 300, that means 24,000. So minus 25,000 plus 24, so obviously it is negative. Then we have 22,000 and here it is 3 into 4, 12,000, and both are basically negative. So what is the value? Not important, it is always negative. Now these both are positive, it is always positive. Don't waste your time doing the full calculation, it is not required, because just see and you will be able to understand whether it is negative or positive. And in this case it is 22,000 and this is 6,000 only, so it is positive. So negative, positive, positive. So 2 negative, 2 positive. So number of non-spontaneous process out of 4, it will be only 2, and spontaneous also 2. Okay. So Helmholtz energy will not be able to finish here, which is another state function, and it is just like del G. Only difference is del G we talk about at constant pressure, but Helmholtz energy denoted by sign capital A, that is considered at constant volume. That is the only difference. Though del G is more important than Helmholtz, but we also have to know what is Helmholtz energy. But as we will not be able to finish it today, so I am not starting it because we are already at the end of the session. Okay, so we are ending it here. Thank you for listening.